Well, hopefully after performing experiment 6.1, you have an idea how the common ion effect works. Basically, what the common ion effect means is that if you're trying to dissolve something into a solution that already has an ion present, included in the thing that you're trying to dissolve, you're going to greatly reduce how much of that second thing is able to dissolve in solution. And you saw that in your lab because you already had sodium ions dissolved when you made salt water. And then when you try to dissolve baking soda in it, which also dissociates into sodium ions, you can't get it to dissolve because there's already so many sodium ions in it, and the solution can only hold so many of them. So today, what we're going to do is we're going to take that information and we're going to explore that mathematically. What does that look like? And can we calculate the amount of ion that is present if I have another ion that's already there? So I'm going to work two problems for you today. And if you've already looked through these samples, you may be going, oh my goodness, this looks complicated. I'm going to show you a technique for trying to organize the information in what's called an ICE table. And ICE tables are actually a very common method used to calculate equilibrium problems. We'll be using them a lot. He doesn't use that technique, but I do find that it's helpful for students to be able to organize the information that they have. So that's what we're going to utilize. So it will look a little different than how he solved it initially, just because I'm going to show you how to set it up a little differently, but the final calculation will end up being the same. All right. So if we look at example 6.5, we've got a solution of lead nitrate, and nitrate compounds are very, very soluble. And so if I have a lead nitrate solution, let's get the example number up here, example 6.5. So I have a lead nitrate solution, and most of it is going to, or all of it is going to dissolve. I just need a single-headed arrow. So I'm going to end up with lead ions, and I'm going to have, whoops, I wrote that backwards. Going to have nitrate ions. Okay, now the problem tells me that it is a 0.1 molar lead nitrate solution. So the lead is 0.10 molar. What does that mean the nitrate solution, the nitrates are in solution? Well, there's twice as many nitrate ions as there are lead ions, so the nitrate ions are going to be 0.20 molar in solution. Okay. Do I need that? Well, maybe not yet, or I might need it in another type of problem. So I do like to go ahead and analyze what's going to be present in the solution. All right, now I'm going to try to dissolve the lead fluoride. And so when I look at lead fluoride, it is not very soluble. And so this is going to set up an equilibrium, and not all of it is going to dissolve. So again, I'm going to have lead ions. And this time I'm also going to have fluoride ions. Okay. Just as a matter of terminology, this is called a net ionic equation, which means that I'm only looking at the ions that are important in the reaction that I'm studying. Okay. There are other ions in solution, but they don't have anything to do with what is going on here with this dissolving process. And so those are called spectator ions. And so in this particular situation, my nitrate is going to be spectator ions. I don't know if he ever mentions those terms, but they're certainly terms that you're going to see again. So I wanted to make sure that I brought them up in case I had forgotten to mention it before. All right. Now, we need to analyze what kind of ions I have present here. So this is where the ICE table is going to come in. ICE, I-C-E. So I'm going to build it underneath this equation. And the first thing I'm going to look at, I stands for initial. What is the initial state going on here? Well, initially, the lead ions I have in solution came from the lead nitrate. So initially, I have 0.10 molar concentration of lead ions. Initially, I don't have any fluoride ions at all. They're not there, okay? Now, as I put the lead fluoride in and it starts to dissolve, what kind of change is going to take place? That's the C in ice. What kind of change am I going to have? Well, I'm going to add X amount of lead ions, and I'm going to add 2X amount of fluoride ions. Because remember, I have twice the number of ions here as I do over here. So therefore, at equilibrium, once that equilibrium gets established, which is what the E stands for, this is going to be 0.10 plus X, and this is going to be 2X. Okay? Now I can look at the KSP expression. So KSP for the lead fluoride, they told us it was 3.7 times 10 to the minus 8th. And equilibrium expression is the lead ions times the concentration of the fluoride ions squared. Okay, so now I can take these two values and I can plug them in here. So I'm going to have 3.7 times 10 to the minus 8 equals, my lead ions are 0.10 plus X, my fluoride ions are 2X, that quantity squared. Now I have a mess because 2X, the quantity squared, is 4X squared, and I'm going to multiply that times X, which is 4X cubed. Solving a cube root? I don't think I want to do that. I think I'm just going to take my ball and go home. If you guys are okay with that, we'll just not do this, okay? Well, no, we actually can't do that. Sorry. But we can make an assumption that is going to make this problem much easier to solve. We already know that lead fluoride doesn't dissolve very much because this KSP is really, really tiny. What if it were the case that such a small amount of this dissolves that it's not really going to affect this very much? And it doesn't end up mattering how much of it dissolves because it's so tiny. Well, that will work as long as I know how big this can be before it matters. And so what we're doing when we make this assumption is we're looking at the rules for addition for significant figures. If I add something that's small enough, then I'm not going to have an answer in my addition problem that goes out any further than the hundredths place. Okay, so therefore, because it would get dropped off with significant figure rules. So therefore, as long as X is smaller than 0.005, I'll be fine. If it's 0.005, if I take 0.10 and add 0.005, then that's going to be 0.105, and that's going to round up to 0.11. Well, then I just affected it, didn't I? Okay. But if this is smaller than that, so if this were a 4, and then this was a 4, and then I rounded it to two significant figures, this is now 0, and so it didn't affect anything. Okay, see, that's where the assumption comes from. I'm using the significant figure rules to make that assumption. So if this has two figures, then this goes out 3, and you make that last number 5. That's how you make that assumption. As long as it's smaller than this, I'm okay. So I'm going to kind of cross that out of there and say, I'm going to assume that that's an okay assumption. I'm going to make the assumption that it doesn't matter, and I'm going to solve the equation and see where I end up. Okay, so once you do that, once you make that assumption, now you have 3.7 times 10 to the minus 8 equals 0.10 times 4x squared. And I'm not going to do all the algebra there, but once you solve that, you end up with an x of 0.00, how many zeros did we have? 0.00030. Okay? Is that smaller than this? Yes, it is. And because that assumption was an okay assumption to make, I know that I don't have to go back and worry about anything. And so the question had asked me what the fluoride ion concentration was. Remember that the fluoride ion concentration is twice whatever X is. So what that tells me then is that the fluoride ion concentration is 0.00060 molar. Okay? So when I'm working with common ion effect, again, I'm going to use an ICE table to figure out what the situation is at equilibrium. I'm going to use my equilibrium expression to plug those values in. And then if I end up with something messy, I make an assumption. And then I've got to check and see if my assumption is or is not okay. When he works example 6.6, the first part of that example is very similar to this one. In fact, that one's even easier because he does sodium hydroxide and there's no exponents there to deal with, so you don't have all that stuff to worry about. So that one's actually easier than this one. But what happens if you make an assumption and it's not okay? I want to go through an example like that with you so that you can see it. So this is going to be the second part of example 6.6. So we'll make some more space here. And start over. All right, so example 6.6, part B. All right, this time we have a 0.030 molar solution of calcium chloride. I'm trying to dissolve thallium chloride in it, and they want to know what the thallium ion concentration will be. So if I have a calcium chloride solution, and here again, I'm assuming that it dissolves completely because they said it was all in solution. So it's a single-headed arrow. So I've got calcium ions and I have chloride ions, okay? They told me that it was 0.030 molar in calcium ions. So therefore, what is it in chloride ions? Well, it's twice that, right? So this is going to be 0.060 molar in chloride ions. All right. Then I've got the thallium chloride that I'm going to try to dissolve that into. So my thallium chloride will set up an equilibrium because it's not very soluble. So I'll have a thallium ion and a chloride ion. And so here again, I'll use my ICE table. So I have initial, change, and equilibrium. So initially, what's the case? Well, initially I don't have any thallium, but I do have 0.060 molar chloride ions in solution. Okay. Once the thallium chloride starts to dissolve, I'm going to add X thallium ions and I'm going to add X chloride ions. Okay. Coefficients are 1, so now I just have single X's down here. So at equilibrium, my thallium concentration is X and my chloride is 0.060 plus X. Now I can plug that into my equilibrium expression. So KSP equals 1.9 times 10 to the minus 4. And I'm going to have thallium ions and chloride ion concentrations to finish that up there. So now I can take these concentrations and I can plug them in. 1.9 times 10 to the minus 4 equals thallium ions are X, chloride ions are 0.060 plus X. Okay. Now, if I multiply that out, that will give me an X squared, but even if I have an X squared, that still means if I can't factor it, I'm probably going to use the quadratic formula, and I'd rather not do that. I mean, I don't enjoy using the quadratic formula. I don't know about you, but it's not one of my favorite things to do. So I'm going to try to make the same assumption that I made before. So I'm going to assume that this X is small enough that I can drop it out, that I don't need it because it's going to be such a small amount of thallium chloride that dissolves that it's really not going to make any difference. So if that is the case, what does X have to be less than? Well, here I have 1, 2, 3 places after the decimal point. So X has to be smaller than 1, 2, 3, and then put a 5 on it. X has to be smaller than this in order for this assumption to be okay. Okay, so let's assume that I drop that out of there. And so when I do that, 1.9 times 10 to the minus 4 equals x times 0.060. And when I solve for x now, I end up with 0.0032. Is my assumption okay this time? Is this number smaller than this? It is not smaller than this. So now my assumption is absolutely not okay. And I'm going to have to go back now and I'm going to have to solve this equation the hard way. Okay. It's not going to factor. It's not going to be a pretty equation to factor at all. So let's go back to this initial equation and let's figure out what this is going to be. Okay. So I'm going to have 1.9 times 10 to the minus 4 equals x times 0.060 is going to be 0.060x, and then I'm going to have an x squared here plus x squared. Now, if you remember when you use the quadratic equation, you need to get this equation into standard form. So to put this in standard form, it's going to be x squared plus 0.060x minus 1.9 times 10 to the minus 4th equals 0. Okay, so there's standard form. Remember, that's A, this is B, this is C when I go to use the quadratic equation. Again, remember that the quadratic equation, I'm just going to get this out of the way because we're going to need the space. Quadratic equation is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Hopefully you remember that. If not, you'll have to go back and pick that up. So now I can take these and plug them in here. Okay, x equals negative b, so that's negative 0.060 plus or minus the square root of b squared, so it's 0.060 squared, minus 4 times a is 1 times a negative 1.9 times 10 to the minus 4th, all over 2a. Yuck. All right. So I'm going to solve what's under the radical sign first. When I do that, that's going to give me negative 0.060 plus or minus the square root of, or plus or minus, because I've already taken the square root, plus or minus 0.066 all over 2. Okay? You're going to have two solutions because you got a plus or a minus in there. But just like when we talked about taking the square root of something before, when you take the square root of it, you're going to have one positive number and one negative number. But because we're dealing with concentrations of solutions, the negative number doesn't make any sense. And so when you solve this, you're going to end up with a positive and a negative, but the negative number, we're going to ignore it because it doesn't help us. I can't have a negative concentration. So the positive number that I get out of this is 0.0030. And so because that's X and because they asked me for thallium ion concentration and that's what X is, then that's going to be my final answer. Okay? They will not give you any problems in the book where you cannot use the simplifying assumption unless you can use the quadratic formula also. Okay, they're not going to ask you to solve anything with a cube root or anything horribly nasty like that. You may have to use the quadratic equation a couple of times, but if you do, that's how you're going to do it. So again, you're going to set up your ICE table so you can figure out what kind of concentrations you're dealing with in solution. Make sure that if that you're watching your stoichiometric coefficients to make sure you're doubling things where that needs to happen. Remember the first problem we did, we had 2 x's in place of regular x's, so you've got to watch that. Set up your KSP expression. Ask yourself, what assumption am I making? Can I make that assumption? What does x have to be smaller than in order for that assumption to be okay? If X is okay and you can just knock that out, then solving this equation is easy. If your simplifying assumption is not okay, then you're going to have to go through and use the quadratic formula. So I've tried to give you plenty of time to work through some of these problems. Some of them are just plain time consuming. So I'll let you get to work on that.